Welcome to all listeners to another FSC Radio podcast episode. I'm with Nina joining us today to talk about one of the biggest mysteries in the universe. Scientists claim that it exists, yet they fail to give an answer to what it is. They claim it really is abundant in the universe, yet they still struggle to get even the tiniest amount. So today, we're accompanied by an expert who will at least try to make it so we leave this podcast today knowing a bit more about dark matter. Welcome, Dr. Aalbers.
Hey, thank you guys for inviting me.
So, Jelle Aalbers.
Yeah, please say Jelle, that's fine.
Good to get
Nice
that
to
out of
have
the way.
you.
Thank you for coming once again. So please tell us a bit, what do you do in this university?
Yeah, so I'm Jelle, and I work on dark matter. I try to find it. I've so far failed, but happy to tell you guys a bit about it. And I also really like teaching, so I teach several courses on programming, subatomic physics, so nuclear physics, particle physics, electricity and magnetism, and a bit of deep learning AI stuff. So
pretty broad.
yeah, indeed.
So how is it that you landed on physics? How did you arrive to this place?
Right. Yeah. So, like, I guess many of my colleagues, we all follow a bit of a winding path, go through different things. So I started as an undergrad studying university college in Utrecht. So that means you've got a pretty broad choice of what subjects you'd like to do. And I was most interested in physics and philosophy. And eventually ended up studying physics for my master after this. Was really captivated by the big mysteries of how the universe works, how the very small and the very large connect. So I studied theoretical physics for a bit. Did a master there in Cambridge and Utrecht. And then I sort of realized that, I don't think I can make a big contribution as a theoretical physicist. Maybe I'm not smart enough, or maybe this is not my field. So I switched and I went into teaching. So I taught in high school for 2 years, taught physics. It's a really nice thing to do. It's really rewarding to sort of represent all of this material that you've learned now to new people and tell them, the basics of how things work. But eventually drawn back into science again. So started my PhD on the subject that I continue to work on to this day. So a few postdocs in between before I landed here in Groningen.
You said you were interested in philosophy. Is that something you would be doing if you weren't doing physics? Or is there something else that you're interested in?
So that's a hard one. So, I mean, doing philosophy, what does it mean, right? I mean, it's thinking in a certain way about problems and about certain specific problems. So I guess many of us do philosophy, but doing it for a job is a whole other matter, right? So that really requires a level of dedication and a lot of specialty, which I don't know if that would have fitted me as well. But sometimes I wonder if something like more philosophy of science or something would have also interested me. But I think physics is a better fit for me. I also really like coding and just doing data analysis. And now I can combine the two. I can analyze the data that we take with our experiments to then say something about the universe, or not say something about it if you don't find anything. So I really enjoy that.
Was it difficult the change from teaching in high school to then going to a PhD? Because for a lot of people it feels like PhD is the next step for a master, but you come from a different place. Yeah,
so I think it was very valuable for me to have worked a few years before I started my PhD. And it also helped that I was sort of switching anyway from a theoretical master to an experimental research project. So that was already a switch. But of course it's... you have to go on the job market and send out letters and hope that someone takes a chance on you. And I was very fortunate that someone did. And I think it worked out in the end for everyone. But at some point you have to say, I don't want to keep doing what I'm doing until I retire, right? And that's a hard choice because you're having also still fun while you're doing it. But at some point I realized that, hey, if I'm going to do this job full time until I retire, then it's not going to be so nice for me. So I know many of my colleagues do, and teaching is still one of my passions. So I'm happy that I can now combine it with research at the university.
Yeah, I was going to say it is nice that you can still continue teaching classes in the meantime. Yeah.
Mm-hmm. So now getting a bit more started into the topic of today's podcast. Mm-hmm. So please tell us about what is, if you could resume it a bit shortly, what is dark matter?
Right, dark matter. Okay, so I think it's a huge unsolved problem in physics. What it is, it's in the words, right? So it's dark and it's matter. So in the first place, it's matter. So it's something. It's some kind of stuff. It can be more in one place than in another place. It participates in gravity, just like everything else. So it's some kind of stuff that's out there in the universe. There's actually a whole lot of it. There's like 5 times as much as ordinary matter, or that ballpark. It depends where you look in the universe. Do you look at the universe as a whole, just at the galaxy? So it's matter, but it's also dark. And we should have really said maybe transparent matter, because what it means is that it doesn't emit or absorb light. It doesn't seem to have any like strong interaction with itself. It also can just pass through regular matter unhindered. So it's a kind of ghost substance that is around. And with all of these things, I should put a little asterisk, and all of this is as far as we've been able to detect. I really hope that dark matter does interact a little bit with ordinary matter. Otherwise, it's really hard to detect. So that's sort of what I try to do. We try to find that little bit of interaction.
And I know your expertise is really on dark matter, but we also, a lot of people that are very enthusiastic about these topics also have heard about dark energy.
Yeah.
What are they similar? What are the differences?
Right. So in one sense, they're similar that we both don't know exactly what it is, but they are very different. I'd say dark matter is much more like ordinary matter than dark energy is. Dark energy is some kind of stuff that is, we call it homogeneous, so it's equal density everywhere. It's not like there's a little bit more dark energy here than there. And it also doesn't behave like ordinary matter in the sense that, it works very differently through gravity. Dark energy is a kind of stuff that once you have it, it tries to make more space, right? So if you make more space, the universe expands. Because you have more space, you have more dark energy, and that wants to make even more space. It's a very different kind of thing. We're not even sure it's a kind of substance. Maybe it's just a kind of modification of the laws of gravity. Whereas for dark matter, we can really clearly say, okay, there's more here, there's less there. So it's a fundamentally different sort of thing than dark matter, dark energy. You also study it in quite a different way.
So you're saying that it's matter, that it's really hard to kind of to see what it actually is, because it's not really interacting with matter that we can see and understand. So how is it then theorized or discovered? Like, where does it stem from? So thanks for that. I should be really careful with how I use my words, right? Because by matter, I don't mean that it's made out of the same building blocks that we are made out of. Okay. Right? So we're built out of, let's say, protons, neutrons, electrons, and there's various other particles that are like heavier cousins of these particles, or rather the quarks and gluons that are inside the nucleus. But dark matter, we believe, is something else. So then there's a couple of questions, like how did we arrive at this? And it's essentially been a process of elimination. So we've known for quite a while that there should be something extra in the universe. No serious scientist believes that the universe is just stars, planets, bit of gas, and the laws of Newton and Einstein, etc. That really doesn't work, right? That may work on small scales for like the solar system, but as soon as you get to galaxies, let alone cosmology, that's not enough. You need more to be able to explain what you see. And people have known that also for a very long time. So early in the 20th century, we started to get the first observations of these stars move in a bit of a funny way, or these galaxies move in an unusual way. What could cause this? But back in the day, there was a lot of things people didn't understand, right? They didn't know quantum physics, relativity. They had no idea how stars had worked. Right, so in the early 20th century, people thought stars were some kind of, maybe they're hot rocks or something, and they're kind of crushing themselves, and the math doesn't really work out. But they didn't know nuclear physics. They had no idea there were engines built by nuclear fusion. So they weren't really bothered by this. That only came later. So the better our understanding of the universe developed, the more and more of the ordinary alternative came. They were essentially rejected. And what remains is that you need to have some kind of new substance, some kind of dark matter.
That's very roughly. If you want, we can talk more about the different kinds of evidence that we have and the different structures. But yeah.
I think you explained it perfectly for my level of understanding.
Okay. Okay.
So how has the view of this dark matter changed over time? So you said that back in the day there was something strange, but there were many things strange. So back in the day, there were already people saying, oh, there's something that is not ordinary matter, that is something else? Or when was this first theorized?
Right. So I think the first time the word was used was actually by Mr. Jacobus Kaptein, right? So here there's some Groninger connection to that. But he was certainly not the first to conjecture, hey, maybe this motion doesn't work and we need to have some new mass in there, right? That happened already earlier. The pivotal moment, as far as I think, and I think some historians of science agree with me on that, is the introduction of cosmology. So that's the study not of a galaxy or a group of galaxies, but of the entire universe as a whole. So when we got precision observations of especially the early universe, so I'm sure you've heard of the Big Bang idea, that the universe started out much smaller, much hotter, and much more flat, homogeneous. So it's much more the same, much more like a soup, essentially, rather than the chunky reality that you see around you. Once we got to know that, we could really more precisely say, hey, already in the early universe, there's a difference between what you would predict if there were just ordinary matter versus if there is dark matter. And then it at some point becomes really hard to deny that you need to have something else, right? If there's just, it looks like there's some extra matter outside the galaxy, some extra source of gravity, say. Well, maybe it's teapots, or maybe it's some remnants of dead stars or black holes, or there's a whole long list. People have gone through those long lists and crossed out basically everything. But if you know that dark matter was already there in the early universe and it was already dark, that really narrows the list down, right? And you can't have teapots or dead stars because there were no stars yet. You really need to come up with something else. So that's when I think dark matter really became, the thing that we all assume and try to work towards. This
was also the time that, correct me if I'm wrong, that it was a pretty standard view on physics that if you were able to know the beginning of the universe, if you were able to understand where every particle was with every motion, you would be able to predict the future.
Right. Yeah. No, that is indeed, in essence, a bit how it works, right? So we know how the universe started, some initial conditions. So what I mentioned, it was a very homogeneous soup, very dense, very hot. Gravity was there. All the other forces we know of are there. And then we can simulate this in a computer and we can press play and see what it evolves to. We can do some little calculations on paper to roughly approximate what it would be, so that we're sure the computer is not just doing something terrible. But of course, right, the simulation is never going to predict the fact that we are having this podcast here together in the Vera building, right? That there's no way, like even if the laws of the physics were deterministic, as we say, so there's no chance involved, you would need to know everything so precisely that is impossible. So instead, the kind of predictions you make are statistical. So you say, well, I think in this volume of space there could be 5 galaxies, or the galaxies should be roughly have this weight. Some are a little bit smaller, some are larger, but there's not going to be things that are 1 billion times heavier or 1 billion times lighter. So those are the kind of predictions that people make in cosmology. And those agree really well at really many different scales, from the size of the smallest kind of galaxies that we can observe to the whole universe. With a model, it's called the lambda CDM model, the lambda cold dark matter model, lambda standing for dark energy, as you mentioned. And that's an extremely successful model, has been able to predict things we see in cosmology very precisely now for several decades.
So now I have a question that I wanted to make.
Yeah.
Back during the Christmas, I was reading a book, totally unrelated topic, but they were using this metaphor that I want to use here too, that I think was very nice. So it's upon two different moments. First, how Neptune was discovered. When Neptune was discovered, they saw that the rotation of Uranus was different, and then they theorized that another planet was there.
Mm-hmm.
But then the same thing happened with Mercury, where they said the rotation is not what we expect. There must be another planet called Vulcan, but that planet never existed. So this is the book that I was reading was making this different metaphor, saying, well, is it a Uranus moment where something happens, as in, is it an addition to the current theory, or is it a Mercury moment, as it is a change of theory? So what I'm asking is, how certain are we that really the model that we have right now works? As in, how certain are we that we're experiencing a Uranus moment and we're not experiencing a Mercury moment?
Yeah, thanks for the question, right? I also use the analogy between Neptune and Mercury sometimes when I explain dark matter, because there is an alternative theory, or at least there has been an alternative theory to dark matter, right? And that is indeed the Mercury example that you mentioned. The solution to the problem of Mercury was that we needed to adjust the laws of gravity. Until the early 20th century, people had assumed the laws of Newton held, which predict very well the motions of the planets until a certain point. And Einstein came up with the laws of general relativity of curved spacetime and was able to predict gravity much more accurately, predict phenomena like black holes and even things like gravitational waves, so that's waves in spacetime itself, which have finally been observed a couple of years ago. So it's an amazing prediction that, Einstein in 1912 or some people around that made on a blackboard, and then 100 years later with extremely precise instruments fits beautifully, right? That is a huge triumph of physics. So how are we sure that's not the case here, right? So I've been telling you, the way we know that dark matter exists is that the motions of galaxies and clusters of galaxies, that they don't add up. And that is indeed before cosmology came around the case. Well, the problem is that if you change the laws of gravity, you need to change them for everywhere, right? You can't say, when it's solar system scale, then my law of gravity is like this. And when it's cluster scale, then it's something else. And for the universe, I again need to do something else. So you need to find one law of gravity, preferably a little simple one, not one with like a million free parameters, that explains everything. And that's not really going to work, right? So people have definitely proposed this, say like, we just make the law of gravity a little weaker on certain scales or a little stronger. But it does not then explain the phenomenology we see at larger scales. So especially at large scales, those theories do not work. One thing, for example, that they really have trouble predicting, those theories of modified gravity, is how do we get structure in the universe? So as I mentioned, the universe started out extremely homogeneously. So every part of the universe looked almost exactly the same as every other part. It's not the case now, right? So if you look in the sky, you see sometimes there's a little prick of a star and sometimes there's empty space. On a larger scale too, there's galaxies and there's big voids in between them. How does that happen? For that, gravity is the answer, right? You start with maybe a very small bit of extra density, just a little clump of something extra, and that attracts more stuff due to gravity. But that's a little hard if you only have matter, right? So if you have matter and you try to compress it, right? If I try to compress my head, something pushes back. It doesn't say, thank you, I always wanted to collapse with gravity, great. No, and the same with gases and other things. So if you start with the picture of the universe, of the early universe that we can now very precisely observe by looking at the cosmic microwave background radiation, that's the afterglow of the Big Bang. But you say, no, that's only due to matter, right? There's no dark matter in there. You anyway can't describe exactly what we're seeing, but okay, leaving that aside, you don't have the sort of seeds to form these structures. You need dark matter to already be there in the early universe to start this process of collapsing to get the structure in the universe that you have now, right? Because dark matter doesn't push back when you compress it. It doesn't, if dark matter starts to collapse under gravity, great, right? It doesn't interact with itself. It can pass through each other, no problem. So dark matter formed the seeds of the structure in the universe that we see today. And that prediction is really hard to get with modified gravity theories.
Wow.
Okay.
Yeah. I got completely lost in the...
I'm sorry. Okay.
So... No, but I was very intrigued.
Okay. Okay, but what can I explain more about this?
It's like if it's pretty mind blowing. All these things. It's really difficult to imagine.
Yeah.
But But all in all, I think sort of in general, your point came across that there's just like so many arguments in favor that the theory holds. We just need to understand like what dark matter really is. Like it's sort of, I think your point sort of came across. It was just like, it was so much, but it was really, really fascinating. But then people like you have been trying to like really, really look onto what dark matter really is.
Right.
But then what proof do you have of this? You said that like if it collapses towards gravity, then it is nice to be with each other. So then that is different from what we observe. But then how do you observe? How do you say, you said before that there are places where there's more dark matter than others. How do you know that?
Yeah. So in terms of proof for dark matter, I can interpret the word proof in different ways, right? So the question is always, what's the alternative, right? So what alternative theory are you going to bring to me that explains our observations? So if that alternative theory is just planets and stars in the laws of Einstein, then I have a very easy time, right? Then I can just point you to any sort of group of galaxies and their motion and show you, look, guys, it doesn't work at all. A harder one is if you come to me and you say, no, maybe the alternative is, okay, there's extra stuff out there, but it's just made out of ordinary matter, right? It's black holes, or black holes are not that ordinary, but okay, let's say it's other dead stars, like neutron stars or something. Well, then my argument is, well, look at our cosmology data, right? So if you say it's dead stars or teapots or whatever, then why am I already seeing deviations very early on in the universe when these things couldn't yet have formed? Right. So, we have several lines of arguments in the early universe. Cosmic microwave background I mentioned. You can also look at the process where different nuclei were made. So the universe didn't just start out in the composition that we have now. Right. There was a little bit of nuclear fusion already happening at the beginning, formed a little bit of helium and heavier elements out of the hydrogen. Already there, you can see that things don't work if you assume all the energy is in ordinary matter. So that's if your alternative is, it's just some kind of regular matter that we already know. And then finally, the harder one is where you say, no, it's some kind of modification of the laws of gravity, right? So then you really have to look at, okay, can you, with a relatively simple modification, explain the observations at all different scales, from the very early universe to just things that we see in a few galaxies? The answer is you can, right? If you make a difficult enough modification of the laws of gravity, you can explain everything. But at some point, you've just made dark matter and called it modified gravity, right? You can at some point make the theory do whatever you want. But how would you explain, for example, that sometimes the source of gravity seems to be somewhere where there is no matter at all, right? You can sometimes have this when two galaxy clusters have collided. Then we can see that much of the gas in those clusters it's really collided, so it's slowed down, it's now in the center of the thing. But if you look, how is the light bent around that cluster, right? Light is bent by gravity just like everything else is. You can see that the mass is not in the center, but more in the outskirts, right? So then, like, how would you explain something like this if you just tweak the laws of gravity? So what's the proof? It depends on what the alternative is. But many of essentially all the really good alternatives have been rejected. I'm happy people are still coming up with them. It would be great if you could do something simpler, but that's not. So it seems really possible.
This really is falsification of Karl Popper to the extreme.
Yeah, in a sense, right? You falsify the alternatives, and then you see what's left. And you also look a bit at so how hard is it to make a theory of dark matter, right? So you need some kind of new particle beyond the standard model. Well, there's many ways of doing that. There's many theories in physics that predict new particles, and many of them lead to exactly what we're seeing, right? So you just need some kind of new particle. There must be enough of it, and it mustn't move too quickly, otherwise it smears out all the structure in the universe, and you end up with what we see, right? So it's a very generic prediction of this set of dark matter theories that you get the universe that we currently have. Whereas if you say, let's do something completely different, then you can also you need to really fit it precisely to what we see.
Mm. I had a question about something you said now, and also maybe earlier, about extending the laws of gravity.
Yeah.
What do you mean by that? Because I wouldn't really intuitively think that you could do that. Because the law of gravity is the law of gravity.
Exactly.
So
Yeah, so you're right? So there is some way that gravity works, that any sort of mass or energy or things related to it attract each other.
Mm-hmm.
We have a law to describe that interaction. It's been formulated by Einstein, and to the best of our knowledge, that law is accurate. We know it's not perfectly accurate. At some point, it has to give way to sort of a quantum theory of gravity, and we don't know what that is because we would need observations that are well beyond what we can actually observe. Right? Ultimately, laws are something that we think of. The world does not speak to us and tell us, hey, here are the laws. That would make our job a lot easier. These are things humans make, and then we have to go out and check whether that actually matches the observations. So what people in the past, and some people are still trying to do, is to say, well, maybe the law of gravity is actually a little bit different. And that may explain some of these things rather than dark matter. And as I mentioned, that doesn't really work at all scales. And there's several things that are really hard to predict that way, unless you make it so complicated that you've basically made dark matter by another name.
Right, okay.
Mm-hmm.
So it's not like the one that we have now is not as universal as we thought, I guess.
Well, yeah, that is sort of the thing that people are trying. But
okay.
Yeah, we've had, for example, these observations of gravitational waves, right? And they really beautifully confirm Einstein's theory, almost disappointingly good. It would be great if we had at least a little bit of a hint of what new gravity theories there might be, because gravity is really fundamental, right? It's about the nature of space-time, and so it'd be really cool if we had a hint of some new gravity theory. But so far, Einstein is doing great.
So we have all heard when we were young and maybe later on that matter cannot be created. It only changes its shape.
Mm-hmm.
Does it also apply to dark matter?
I would say it's wrong. I think matter can be created. I think you're creating matter right now. You are emitting infrared photons, right? So that is a kind of matter that is being created. But also electrons, protons, neutrons, these things can be created, right? There are right now cosmic rays from space, which are often, for example, protons or little hydrogen nuclei that have lost their electron, bombarding the atmosphere. And there's a whole shower of particles being created in that process, right? So it is one type of energy being converted into another type of energy. So it's energy in motion being converted to energy in particles, in mass, right? That's E is mc squared. So you can definitely create matter. There's some limits on it. I cannot make for you out of nothing 100 electrons and nothing else, right? That first of all, if it's out of nothing, you have to deal with energy conservation, right? Where you get this energy from, you got to pay for it somehow.
There's always a trade-off.
Yeah, and you got to deal with charge conservation. So I'm making 100 negative things. I also got to make 100 positive things at the same time. Or find another universe, because our universe has conservation of electric charge. Okay, but that's the first point. Now you're talking about dark matter. Absolutely, dark matter needs to be created, right, at some point. That's at least what we think, right? We think all of the particles that exist in the universe were created somewhere in the early universe. Like initially you had a mostly empty universe, and in a process that's called inflation, it really expanded quickly, and that's sort of the energy in that expansion eventually came to form lots of particles. The details of this are not fully understood, by the way. This is not as solid as, for example, the laws of gravity that I've been telling you about. But that's at least the current theory. So then you should also make these dark matter particles. If you do that, then for a specific dark matter particle, and so if you come to me and say, well, I think dark matter is basically like a proton, but with a little bit of different things. Okay, good. Now I can maybe predict how much dark matter you make, right? So I know how we started off in the early universe, how much of all the other particles there were. Then if you tell me specifically what your dark matter is, I should find out how much dark matter is produced in that process. So that is one of the things we can use to constrain the fantasy of theoretical physicists, right? They think, maybe dark matter is like this or like that. But if you produce 10 times as much dark matter than we actually see, too bad, right? Your theory is wrong. So come up with another one.
So there are some constraints in this sense.
Absolutely, yeah.
There is one when I was preparing for this, there was one sort of articles that I came across, not necessarily academic articles, but it was talking about, and you need to correct me if these were just very alarmist and they were not really telling the truth, about that the astronomy was sort of in crisis. So there were many things. For instance, they were talking that they have found in the universe that the universe doesn't seem to be as homogeneous as we thought. That you have spans of giant arcs of galaxies, and then also places where there are very little galaxies compared to what we expected, which to some extent violates the cosmological principle, which assumes that we can get ideas from the universe from here. Mm-hmm. There were also the Hubble constant is starting to give different values, even though they keep repeating the same measurements via different methods. They get one value, and through another method they get another value. Mm-hmm. And then also about baby universe, like the very early universe, with pretty old galaxies. That the Lambda CDM model that you talked about predicted that the galaxies will appear after 500 million years, but there has been observed some galaxies that were formed 280 million years ago, or at least they claim that some galaxies were made then. Also, some carbon and nitrogen were found in this, which does not really correlate to what we see. So let me ask you, what is going on here? Is this all just people being very alarmist and it's not that deep, or is it actually that there is a big crackdown in astronomy?
It's a nice question, right? So I haven't received a code red email in my inbox telling me that this crisis, you guys need to work harder or something. We always try to figure out things, and this is just a partial list of the problems we have.
I know there are many more.
You can go to the Wikipedia list of open or unsolved problems in physics and astronomy. There's always problems. I think Feynman said something like this, that if you go to the edge of science, it's always messy, there's little things sticking out, it doesn't all fit together. I think that's very much the case here, right? So I think our fundamental theories of the universe are very solid. We have multiple pieces of evidence from different scales that agree with it very well. Disappointingly so. I think if there is a crisis, that is more the problem, that we are lacking clear guidance from data on what the new sort of theories should be. You are right, though, that there are always, I think at any point in science, some pieces of data that seem to not fit the puzzle. I've had with my experiment, which maybe we'll talk about later, also had at some point we had some observation that we couldn't really fit. We thought, maybe it's dark matter, maybe it's something else. Very often what happens is that a few years later you figure out that something wasn't properly screwed in, there was some extra background in your detector. When you looked at galaxies, you hadn't taken into account the dust that happens in between properly. Science is a process where these things gradually get more accurate. You mentioned the Hubble constant, right? So we now measure the Hubble constant much more accurately than we could do decades ago. And there are disagreements between astronomers on which particular value it needs to take.
But could you explain real quick what the Hubble constant is?
Right, so the Hubble constant is something that describes the speed at which the universe expands, right? So the universe is still expanding, right? So in that sense, you could say the Big Bang never really ended, although the period of accelerated expansion is definitely over, right? That happened only very early on. I should say that's on the large view. There is now, again, accelerated expansion, but it's much slower accelerated expansion than we had in the past. That's, again, related to dark energy. So it started off with accelerated expansion slowed down, and now it's slightly accelerating again. Right. So the Hubble constant describes the speed of the expansion of the universe, so how fast different things move away from each other when they're at a large distance from each other. On average, you could always have a little bit of extra motion that's just caused by whatever things are in your neighborhood. So you can measure that in different ways, right? You can basically look at faraway galaxies, see how far they're moving away. That is not so easy as it sounds, right? You need to determine how far away they are and the velocity of these things. So astronomers and cosmologists have constructed something that's called a distance ladder, whereby we use one method in astronomy to measure distances up to a certain point. And we have another method, which is maybe less accurate, but can be used for distances further away, that we can calibrate with the earlier method. So we just have different methods, and these we can chain together to get estimates of very far away things. So that's one way. The other way is looking at the early universe and precision measurements of the microwave radiation. There's other ways, right? We just talked about gravitational waves. They give some information on the Hubble constant. We haven't yet gotten enough of those that we can give a precise estimate of the Hubble constant based on those. But yeah, these are different ways, and currently they're giving slightly different answers. And it is very interesting and a continued source of debate how those could come. And there are proposals for maybe some new physics effects in there, but those are definitely not the only proposals. There's many people you can talk to that say, no, this is just because of some particular systematic effect. And another astronomer says, no, we've looked at that 100 times. And then you can have a fight between them. And that's often the way it is in science, right? I'd love to be able to say that you just need to make one measurement and that completely refutes or confirms one theory. Not how it works, right? There have been many people who claimed detections of dark matter who later had to say, yeah, actually, maybe not.
If only were that easy.
Yeah, exactly. Mm-hmm.
I actually had a question, which maybe diverts from this a little bit. Mm-hmm. And my knowledge of physics is limited, let alone, talking about string theory. But
my knowledge is also very limited on things.
But I was curious if there is some kind of maybe, theorizing or relationship between string theory and dark matter.
Right. So string theory is a candidate theory of everything, right? Mm-hmm. So I just mentioned that we have a very good theory of gravity, Einstein's theory. We have a very nice theory of everything other than gravity, right? That is called the standard model of particle physics. That includes electricity and magnetism, but also the nuclear forces and all of the other kinds of funny particles that you can make in the universe that we know of, including, for example, the Higgs boson you might have heard of, which was discovered not too long ago at the Large Hadron Collider. So this works very beautifully, but gravity does not so easily fit in the same framework, right? So this is made in a framework called quantum field theory. Gravity is a classical field theory. There's no quantum effects in there. You can make quantum field theories of gravity, but they usually have some kind of problem. Like they might not predict what happens at very high energy, for example. So we don't really know how to combine these things. String theory is a framework in which you can make those theories. It's not, this is the theory that is uniquely specified, but it is one way that you can make these theories. So if it's a theory of everything, then of course dark matter has to be explained as well, right? Otherwise it wouldn't be a pretty good theory of everything. But string theory is a much more speculative business than dark matter is. Dark matter is something for which we have a lot of specific evidence against many types of alternatives. For string theory, I think opinions differ. There are people who say that we might be able to get hints of certain forms of string theory, but I think it's fair to say that this is, mostly very interesting, but still speculative.
Yeah, very theoretical, mysterious.
It's a theory, and there are other theories. There are quantum theories of gravity that are not string theory, and it's a hard question. Like, how are you actually going to decide between these things? There are also many theories of dark matter, and we have experiments, like my own experiment, that is capable of distinguishing between some of these theories. But making such an experiment for string theory is much harder.
So far, it's just in the theoretical realm, the string theory. So what do you do? What do you do to try to get to know what dark matter is?
Yeah, so we try to catch it, and we use a big tank of xenon, right? So xenon is a noble gas. Okay. We put a big tank of this underground. We liquefy it. So we have just a big cylinder of this liquid xenon. And then what we hope is that dark matter has a little bit of interaction with ordinary matter, right? Maybe it has only gravity, then our whole experiment is pointless, right? We're never going to see anything too bad. But if it has a little bit of interaction with ordinary matter, then maybe once or twice a year, we get a little bump onto one of our xenon atoms from the dark matter that is surrounding the Earth and the galaxy. And that will then, because the xenon has been set in motion, the xenon bumps into its neighbors, you get some light, you get a bit of charge liberated, so you get a little flash of light in this tank of xenon.
So a bit about the experiment. Why xenon?
Why xenon? Yeah. So in principle, we think if dark matter has an interaction with ordinary matter, we don't have specific reasons to think it'll interact more with, say, protons than neutrons, etc. But xenon is a pretty heavy element, not as heavy as lead, for example, but much heavier than hydrogen or oxygen. So there's a lot of protons and neutrons packed really closely together.
Because it's also a noble gas, so it's pretty small compared to other atoms. Xenon. It's true that it's very big, but it's a noble gas, so then it has
right.
the octet.
Yeah, I guess you're right. Yeah, so the density is pretty high, right? So it's a pretty dense thing, right? Because I guess its atomic radius is small. But yeah, the real benefit comes from just the nucleus, right? So the nucleus is much smaller than the atom itself, like a factor 100,000. Just having many nucleons, so protons and neutrons close together, that really enhances the probability of dark matter colliding. And that's actually a quantum effect. It's unintuitive. You might think, okay, if I have a chance of something bumping into a ball, and if I put 100 balls together, now I have 100 times more chance, right? Or maybe even less, right? Because maybe some of the balls are shielding each other. For dark matter, that doesn't work because dark matter usually passes through everything. That's actually not how it works. In quantum mechanics, you get 100 squared times the probability, right? So you get a kind of effect that is interference, right? So that's because, things just work differently than they do with particles. You have to describe them with a kind of wave mechanics, and then you get this phenomena. We're not going to do an introductory quantum mechanics lecture here, but safe to say, it really helps to have lots of nucleons, protons and neutrons together. So that's one reason we pick xenon. But then why don't we pick lead, right? Lead is much more...
or uranium.
These things. Uranium, even better. Okay, so uranium, let me tackle that one first. What's going to happen if I put a lot of uranium?
It's going to decay.
It's going to decay, yeah. So there's always going to be emissions of a little bit of light and charge. So there's going to be a huge background. In fact, that is the case with almost any element that you pick. Many elements have radioactive isotopes, so there's like little variants of that element that are radioactive, that are just around, right? If you think, for example, of hydrogen, you have hydrogen 1, which is fine, deuterium, which is also fine, tritium, which is not fine. That decays over the period of a few years, and it gets continuously produced by these cosmic rays and other things. So yeah, that's our main challenge, this making it completely free of radioactivity. That's our enemy, radioactivity. And xenon is an element that doesn't have many radioactive isotopes, and it's also an element in which you can make these signals visible. If I just have a giant block of lead, then how am I going to get those light flashes out, right? So in liquid xenon, that works extremely well. So there's a couple of things why we use xenon. You catch a lot of dark matter, there's little radioactive background, and I can make the signals really visible. That's why I pick xenon.
How big is this tank?
It's a couple of tons, so it's the size of a person. It's not that big, right? There's detectors out there that have thousands of tons of water, and for example, but those are not usually dark matter detectors. They look for something else. I wish I could make a couple thousand tons xenon detector. Guess what the problem is?
The budget.
Yes.
Money, right? Xenon is per weight more expensive than silver. So this is it's very difficult to get a lot of it. And that's also what limits ultimately how big we can build these things.
So this experiment, it was you that when you came here, you set up, you theorized, or when you came here, it was already in place and then you took over the project?
Right. Neither. So science these days is done in very large groups of scientists. So I have a very small role in this experiment, which I'm nonetheless very happy to do. But think of like a couple hundred people that are doing this. And that is a very small experiment by the standards of modern science, right? If you talk to my colleagues working on the Large Hadron Collider, you start talking when you have a couple thousand scientists together and, a couple of billions. And we are still orders of magnitude smaller than this. Also, you don't just start by going to your local politicians and say, hey, I'd like $100 million and I'm going to buy xenon with it, right? That doesn't work. What does work is you first, you may have some money from your university and you build a tiny thing with 10 kilograms, right? And then you place it underground, you look for dark matter, you don't find anything, but here's the key, you can exclude lots of theories that would have predicted you see something, right? So there's lots of theorists making models of dark matter, and some of these theories say, if you build that thing, you're going to see it. And then we're both happy because I get the Nobel Prize because I predicted it, and maybe you too because you saw it. And then we're both happy. So we build the thing, we look, there's nothing.
So then that's how you get articles, by
Yeah.
Disproving other people.
Exactly. That's our job, right? Making theorists unhappy every year, right? That's what we do. That's falsification, what we said. That's exactly what we do. So then you've built your tent on thing. You've made some theorists unhappy. And now you go to your local politicians and say, like a little bit of money, make 100-kilogram thing. We can make a lot more theorists unhappy, or maybe we really discover dark matter. There's a chance, right? And the chance is pretty reasonable. Like especially like several decades ago, there was really the sense that there's a class of dark matter models that you should very easily be able to see with these detectors. And they're called WIMPs, weakly interacting massive particles. And many of those models have been ruled out by us. Not all of them. There's still a couple left, and that's why we're still in business, right? So we're not done yet.
So with this, there are many ways where you can, if you try to look for dark matter, there is thousands of people in the world looking for it.
Yeah.
Why did you choose this path? What's special about this that is not other, like just using using a telescope, like the James Webb Telescope? You could be getting data from it and then try to extrapolate to confirm whether dark matter.
Right. So you're right. There's different ways of looking for. So now we're no longer talking about is dark matter real or not. We're talking about which specific particle makes up the dark matter. And then you've got different ways of doing it. One way is the way I'm doing it, which is try to do it on Earth in a detector, usually underground, so you shield it from the cosmic rays, etc. Another way is to look at, say, faraway galaxies and see maybe can you see a signal of, for example, dark matter annihilating with itself and producing gamma rays or some kind of light, right? So you may have heard of antimatter. So that is, for every matter that exists, you can make some antimatter. And when you put it together, you can make whatever, right? So because you're no longer bound by these constraints that we mentioned. You have, right? I can't make 100 electrons out of nothing, but I can make 100 electrons and 100 anti-electrons, which are 100 positrons. And if I put that together, I've got lots of energy that I can make all kinds of stuff with, right? So the idea is maybe dark matter is made out of dark matter and dark antimatter. So that occasionally the two meet, and who knows what happens, right? You can get light, you can get neutrinos, you can get all kinds of stuff. That you can also do. And there's another way, right? What you can also do, you go to your local particle accelerator, or better yet to the Large Hadron Collider in CERN, smash ordinary matter together really hard, lots of particles get created, maybe some dark matter particle gets created, right? So then that's of course hard to detect, right? We don't have a detector that will specifically detect dark matter. That would be great. Well, in a sense, my detector tries to do it, but it's really hard. Dark matter passes through everything. So what you then do is you see where all the other particles are going. You add up their little velocities, energy, momenta, etc., and you say, hey, there's something missing, right? So something went out that we didn't see. So these are sort of three of the main ways you can detect dark matter. So why am I doing my way? Well, someone's got to do it, right? So these three things are different. There's some models you can test with one way, some with another, and some with another. And yeah, there's certain models that you can best test with my method. Others that work best with the other method. It could very well be that one of these other methods yields success and mine does not. In fact, I'd say that's the more likely possibility, because we're just one method out of many. So that's in a sense a bit disappointing, because you know that you're probably not going to see it, but you're still making an important contribution.
So with these important contributions, when do you think we might know what dark matter is?
If we will ever know.
That is, yeah.
I'm going to give a very disappointing answer, I'm afraid. It's
know.
either tomorrow or never, right? No, sorry, it's just anywhere between tomorrow and never. It's not tomorrow or never, but we have really no idea. It is not so difficult to make a dark matter theory that we will never be able to detect with anything in our current technological arsenal. On the other hand, it's also not so difficult to come up with theories that we could see right now. I think there is a reasonable shot, given how quickly we are making progress in building these detectors, that we see something within the next few years. On the other hand, we've been saying that for a while.
Yeah.
So, I really don't know, right?
The progress is there.
Yeah, it's important to know what progress consists of. It doesn't consist of finding little pieces of dark matter and learning more about it. It consists in ruling out ideas of what it could be. And eventually, well, we hope, of course, to discover something, and then all of the other ideas are immediately ruled out. It's like winning the jackpot. But probably, and in the past, it has been for a long time, that it's just a narrowing down of the fields of ideas. And that's still very significant.
Yeah, of course.
But of course, it's not as big as suddenly discovering something. But that's simply how science works in this day and age. In order to really make progress on fundamental things, you need not only a lot of people, a lot of money, but also a lot of patience.
Yeah.
It's not you can do some easy experiment here in the room that will completely shock the world.
So we've been talking for a while about dark matter, but then my question sort of is for the general people, why should we care about this if we should? Why is this relevant to us?
Yeah, that's a good question, right? Why are you listening to this podcast? Right, what's the point, right? So there's a couple of things. Like maybe you find it interesting. Maybe you'd like to know what the universe is made of. I'd like to, and I'd like to also be able to tell other people this. And I think, in a sense, dark matter is the most embarrassing of this long list of open problems in physics. We've known for a very long time that there is this extra stuff out there in the universe. And we think we are so great. Right? We can predict almost all kinds of phenomena with fantastic precision, except that we don't know what most of the matter in our universe is made out of. Yeah, that's a big deal. I would like to solve that, right? That, I think, is just a great achievement to have. If you ask, okay, is it going to lower the price of milk? Well, probably not directly. On the other hand, if you asked that to scientists 300 years ago, that would also be the case. It would not immediately lower the price of milk. Sometimes it takes a very long time before a discovery actually yields, say, economically useful results. What is much more common is that while we are doing this, we discover new ways of building detectors, of new ways of analyzing data. We train people in cool analysis techniques. We give people a little playground where you can do things without it immediately affecting the lives of people or their health or something. So there's a lot of byproducts that you get from scientific research. Of course, it costs money, but it's a very small amount of money compared to the money that goes to other big parts of society. I think it's useful to have a couple of these scientists around to do weird stuff. I think over the course of history, it's proven that sometimes they come up with unexpected, useful stuff. So I think that's why we do it.
I want to ask more for a general question. Well, you've been talking about general relativity, about the universe, and then how can we predict?
Mm-hmm.
But at the end of the day, right, matter, if you go to the small scale, it just all comes down to what we call quantum physics, right?
Mm-hmm.
That is not it's not a perfect theory, but it works pretty decently. So if we even though when we're looking at the universe, we're looking at the big scale, there's still quantum effects in it that are rather important.
Absolutely, yeah.
So how connected is astrophysics to quantum physics, which might be like a bit of a not dumb question, but like weird question, because quantum physics look at the smallest thing possible, and astrophysics is looking at the biggest thing possible. So how connected are really to these two sort of opposite?
Yeah, no, they're absolutely related. And there's a reason, if you study astrophysics here, that in your second year, you are required to take 2 and several other courses that involve quantum physics, right? Quantum physics is essential if you want to understand anything in the universe. You say it's not a perfect theory. I would actually say we have no evidence that goes beyond quantum physics. The best thing that we can do is maybe gravity, because it's kind of hard to make a quantum theory for that. But there's options to make that happen, right? Quantum physics is amazing. It is super precise. All our modern theories of the world are quantum. You want to understand how stars work, how nuclear fusion works? You need quantum physics. Your other part of the question was, hey, but the universe is about really large things, and quantum mechanics is about really small things, right? So, of course, sometimes the small affects the very large, right? The sun is shining right now. This energy comes from a nuclear physics reaction in the core of the stars, and that affects life on Earth. But the other point is that the universe, the large things used to be very small, right? So the universe started out very small. So, in fact, our theory is that on a large scale at least, the fluctuations that we see in the universe originally happened from quantum processes in the very early universe. So you might say that we are all magnified quantum fluctuations in a sense. Right, so that is, I think, the reason the small and the large connect is because what's large now used to be very small in the past. But quantum mechanics is just everything, right? You want to do any physics beyond just small classical things, you need quantum.
Well, I wanted to ask because there was we're talking about astronomy, and it's true that when you're trying to detect dark matter, you're using a xenon tank.
Yeah.
But you mentioned another way of detecting it, that is using telescopes, and I want to ask because I had a last blog. I had a course with you in Python. That was really nice. And then my TA was Alex, that I know works with you.
Yeah.
But he told me he was talking to me about the sort of the things he did, and it was really interesting. He works with the Hubble telescope, and it was very surprising to me because it's open source. Whenever I just look at these millions and millions that are pouring into science, it's true that then they release academic articles, but his Hubble telescope releases the data that it gets.
Yeah.
So my question is, could you explain a bit what, like, for people to because to me it was really, really amazing to see that this is actually being spread out. So how does this work? How does what is the Hubble Space Telescope? What does it do? What is it so good? And if we can expect improvements of future telescopes.
Sure. Hubble telescope is amazing. I remember looking at pictures of the Hubble Space Telescope when I was a kid and like, wow, astronomy, awesome. All these different colors and different things. So it was launched already many decades ago. It's lasting way longer than we expected after a couple of repairs that had to be done. And it's played a very important role in many fields of science, also dark matter science. But yeah, there's all kinds of branches of astronomy that has been a very important telescope for. It was so important that people said we should have another of this kind of telescope, but better, right? The problem with the Hubble Space Telescope is that it looks in the visible light. That's great, right? Lots of things to see in the visible light. Only problem is universe expands. So if you want to look very far away, that visible light wave that is coming towards you is going to get stretched. So it becomes an infrared wave. And then the Hubble Space Telescope can't see it anymore. So what happens is that scientists built a new telescope called the James Webb Telescope that can see into the infrared light. This was launched, and this has been taking pictures now for a couple of years. And that is also having a huge impact on different branches of science, also just making really pretty pictures. But as you say, one of the amazing things of these programs is because they are so expensive, way more expensive than my little experiment, though still far less expensive than, say, if you want to build a new kind of jet fighter or something. Because they're this expensive and it's paid by public money, the governments tell these scientists, look, you can do your own observations, nice, but the data gets public, right? You need to release this also to other astronomers, that they can then make discoveries with this. And I think that's a really great practice. And astronomy is better at that than my field of... So I'm astroparticle physics, so I'm somewhere between astrophysics and particle physics. Particle physics has historically not been so open, but also because of its larger size of projects, people are more pushing for that. The counter-argument is usually these data are very difficult to understand. If you see a nice picture of the Hubble Space Telescope or the James Webb, maybe you don't even need to understand. It's just an awesome thing to have on a poster, right? For my detector, that is not the case, right? And so very often you need a lot of specialized knowledge to even be able to interpret the data. So we for sure make our research available publicly, right? So our papers don't just go to a paywalled journal, but they also go on a public archive. We often release also some part of our data that other people can easily use. But just, dumping a petabyte of data out there and just saying, you guys figure it out, that is not yet in the tradition of the field.
And there is another telescope coming up in the coming years.
There are many, many kinds of telescopes.
Like the next generation after the James Webb.
I'm not so they're planning different things. You should really ask one of my astronomy colleagues about this. But I mean, these are just, I was talking about like very large space-based observatories. They're also amazing ground observatories. There's much more to astronomy than just visible light and infrared. You can do radio astronomy, right? There's a lot of radio astronomy happening in the Groningen area with Westerbork, Lofar. You can go to the other extreme. You can do gamma ray astronomy. I've got colleagues looking at the sky and these very, very high frequencies. Maybe find dark matter that way, learn about the highest energy processes in the universe. I even sometimes say that I have a telescope, right? My little xenon tank is also looking at dark matter from outer space. We just don't have a very good angular resolution, right? Because we can see things from the entire sky at once. So I'm not sure astronomers agree that we are telescopes, but I think we're kind of observatories of a sort.
Do satellites interfere with telescopes?
Well, not in my telescope. No, but with many other telescopes they do, unfortunately. Especially if you look at what are called transients, so events that are only briefly there, right? So maybe you're looking at asteroids, or you're looking at bursts of activity in stars. The problem is that there's an awful lot of these satellites now, right? If there's occasionally one, there's no problem. We wait till the satellite passes and then we take the picture. But if there's always a satellite in your picture, or if there's always 100 satellites in your picture, it starts to get a problem, right? Radio astronomers have had this problem for much longer. Their problem isn't satellites, their problem is radio. Like, I don't think this particular radio is the problem, but if you broadcast this in different frequencies, then that can interfere with frequencies. So that's why they sometimes go to really remote locations where there's less radio interference. For me, the problem is radioactivity and radioactive backgrounds and cosmic rays. And that's why we go to deep underground. There's a mountain somewhere in central Italy. There's a highway tunnel through it. And halfway through the mountain, you can go left. And you can, or you really turn first left and then right. But okay. Then you come into our lab, which is just in the middle of the mountain. That's where we place our xenon tank. And we hope to see dark matter. So come visit us there sometime if you want.
In Italy sounds good.
I don't mind that.
I guess maybe as a final question, what is your favorite physicist at the moment, or in general, or?
That's a tough one. I mean, I guess everybody who does physics grows up sort of idolizing Einstein, but. Right, this is such a... this is not how science is done anymore now, right? So this... I don't think the idea of worshipping individual scientists is such a great thing to do. That's not just because these are also occasionally flawed characters themselves, although many have also done very good things for the world. But because it doesn't match with how science is done anymore. You do these science in large collaborations where everybody contributes a small bit, and that can be a very crucial bit, like maybe a very cool idea, but it's not just one person on a blackboard that solves it all. And many people think that they're going to be that person, and then they're disappointed, and then they're like, hey, why am I not like Einstein? Well, that's just ain't how it works anymore. You need to come together with a lot of people, pool your resources, pool your talents. And I've had many talented colleagues that I could work with who could make that happen. And so I don't think I'm not that into hero worship anymore, though it's of course very cool to tell in my courses students about the great breakthroughs of the past. But we often, I think the focus on individual figures is a bit limiting, and we forget all of the other people that were around it doing experiments and making their breakthroughs possible.
Yeah. So you admire the work of many physicists that you've worked with or whose papers you've read, and
I realize it's a bit of a cheat answer, but
no, but I mean it's completely fair.
I think so that making these large collaborations possible, making sure that people are happy within these large collaborations, right? You start as a very young scientist here, you have no idea what's going on, everybody's doing something, and then the people that in those collaborations make you feel welcome, make you feel like you're really contributing. I think those are really the pillars that science is resting on at the moment.
Wonderful, perfect answer.
I think it's a pretty unique answer.
Yeah.
Okay.
Yeah.
So thank you very much, Jelle.
Thank you.
Thank you so much.
Thank you for all the information, all the insights about.
Thank you for the great questions.
And we'll catch you guys next time.
See you.
Bye.
Bye.